Every day, over 10 million Snickers, Reese's peanut butter cups, and M&M's roll off massive production lines built with incredible engineering. From molten chocolate rivers to robotic wrappers sealing thousands of bars a minute, each step turns raw cocoa into the world's favorite candy. Today, we step inside the factory to see how these legendary treats are assembled and perfected at astonishing scale. Producing 10 million Snickers bars begins with raw ingredients delivered in industrial-scale volumes. Liquid glucose, granulated sugar, skimmed milk powder, cocoa liquor, cocoa butter, vegetable fats, peanuts, egg white, lactose, and emulsifiers. All materials are stored in temperature-controlled silos, tanks, or hoppers, connected by stainless steel pipelines and pneumatic conveyors to feed the production lines with uninterrupted flow. The first step is the nougat base. A pre-blend of sugar, glucose syrup, and water is piped into a continuous cooker. This cooker operates under controlled heat and vacuum, rapidly boiling the mixture to reach the target solid's content while minimizing color and flavor degradation. The hot syrup exits at around 120 degrees Celsius and is sent straight into a high-speed whipping chamber. Inside the whipper, dried egg white and milk powders are injected. A rotostator system beats the mix at high speed, incorporating air into the matrix to create the nougat's aerated structure. The density is tightly regulated with inline sensors measuring viscosity and expansion ratio in real time. Once aerated, the warm nougat mass flows through heated stainless steel pipes and is deposited as a continuous sheet onto a wide belt coated with a release film. As the sheet advances, calibrated rollers compress it to a uniform height, typically between 12 and 15 millimeters. The sheet then passes through a cooling tunnel that drops its internal temperature below 20 degrees, stabilizing the structure for the next layer. Once cooled, the caramel layer is applied. Caramel production occurs in a separate closed-loop cooker, where a mixture of glucose syrup, sugar, dairy fats, and milk solids is cooked under vacuum to reach the desired viscosity and chew. The caramel exits the cooker at around 118 degrees and flows into a depositing manifold. This manifold lays a smooth, uniform layer of hot caramel directly onto the nougat sheet. While the caramel remains soft, whole roasted peanuts are added. Peanuts, sourced in bulk, are first passed through an inline sifter to remove debris, then lightly roasted in continuous rotary ovens. After roasting, they are cooled and metered onto the caramel layer using a vibratory conveyor with adjustable baffles. The conveyor distributes peanuts evenly across the moving sheet, ensuring every section contains a balanced nut density. The peanut caramel nougat tri-layer now proceeds through a final compression roller, bringing it to the finished bar thickness. From here, the slab enters a chilling tunnel that gradually reduces its temperature from ambient to below 10 degrees Celsius over a span of 20 meters. This ensures the caramel sets just enough to be cleanly cut without oozing or deformation. After chilling, the slab moves to a guillotine cutter. First, rotary blades cut it lengthwise into continuous ribbons, each the width of a Snickers bar. Then, a high-speed guillotine slices each ribbon into uniform bar-sized segments using servo-controlled motion synchronized with the belt speed. Blades are coated with a non-stick surface and cleaned automatically to prevent buildup. Each freshly cut bar now enters the enrobing stage. Bars are transferred onto a wire mesh conveyor belt and passed beneath a curtain of tempered milk chocolate. This chocolate is continuously circulated through a 3-stage tempering system, where it is heated, cooled, and reheated to create stable cocoa butter crystals. The chocolate is maintained at 30 to 37 degrees Celsius, ensuring proper viscosity and flow. As each bar passes through the enrober, it is coated on all sides, top, bottom, and flanks. The base of the bar receives a bottoming layer of chocolate from a pre-flooded section of the belt. excess chocolate is removed by an adjustable air knife that blows a focused jet across the bar's surface, shaping the characteristic swirl patterns on top. A vibrating section under the mesh belt removes bubbles and smooths the surface. The enrobed bars enter a cooling tunnel that spans 30 meters and consists of multiple zones. Each zone gradually reduces the air temperature, allowing the chocolate to crystallize evenly. The final zone chills the bars to below 8 degrees Celsius, locking the coating into a firm, glossy finish with the correct snap and bloom resistance. After exiting the tunnel, each bar is inspected by a vision system. High-resolution cameras scan every unit for shape, surface quality, alignment, and chocolate coverage. Defective bars, those with missing peanuts, air gaps, or surface defects, are automatically rejected through pneumatic diverters. Accepted bars move on to the wrapping section. Each bar is fed into a flow wrapping machine running at speeds of up to 100 bars per minute. Wrapping film, pre-printed with branding and batch codes, is drawn from a roll and cut to size by rotary knives. As each bar passes through, it is wrapped in film, heat-sealed along the underside, and crimp-sealed at both ends. The sealing jaws operate with synchronized thermal and pressure settings to create tight, tamper-proof packages. Wrapped bars are conveyed through a metal detector calibrated to detect both ferrous and non-ferrous contaminants. Any bar triggering the system is rejected. Compliant bars continue to the check weigher, which confirms unit weight to within plus and 1.5 grams. Any deviation results in immediate removal from the line. The verified bars are then grouped and collated. Robotic arms pick up sets of bars, typically 24, 36, or 48, and place them into cartons automatically erected from flat blanks. Hot melt glue is applied by precision nozzles to secure the flaps. Cartons are closed, sealed, and printed with best before dates using high-speed inkjet coders. Cartons then advance to the palletizing station. Here, robotic palletizers arrange the cartons into stacks on standard Euro or GMA pallets, using a pre-programmed pattern that alternates layer direction for stability. Slip sheets are inserted automatically between layers. Once a pallet is complete, it is wrapped with stretch film by a rotating arm that applies the film under tension to create a rigid, transport-stable unit. Throughout the entire process, programmable logic controllers coordinate equipment motion, timing, and feedback across the line. Each machine is connected to a centralized SCADA system that logs production metrics, sensor values, fault codes, and output counts in real time. Operators monitor touchscreen panels displaying temperature trends, motor speeds, belt loads, fill levels, and inspection alerts. The chocolate tempering unit is governed by 3 separate thermal zones, each independently controlled by thermocouples and heating elements. Syrup bricks is measured inline using optical refractometers. Nougat density is monitored by in-pipe density meters. Caramel viscosity is controlled by adjusting vacuum level and cook temperature. Every variable is closed-loop controlled, meaning it adjusts itself based on sensor readings. Carbon dioxide is used in modified atmosphere packaging for bulk storage formats. The gas is injected into large multi-bar containers to displace oxygen, extending shelf life. These containers are flushed, sealed, and stored in chilled holding bays before being distributed. Clean-in-place systems automate sanitation. Heated caustic detergent flows through all nougat, caramel, and chocolate handling systems at the end of each run. Pipes, tanks, depositors, and pumps are cleaned in sequence, followed by hot water and sanitizing rinse. Each cycle is logged with flow rate, contact time, and temperature. To produce 10 million Snickers bars, the line operates continuously for multiple days across several parallel lines. A single high-speed line can produce up to 1,100 bars per minute. With 10 such lines running in tandem, nearly 720,000 bars are produced per hour. In under 14 hours, 10 million bars are complete. Each bar is mechanically identical. Same mass, same shape, same structure. From aerated nougat to sticky caramel, crunchy peanuts, and smooth milk chocolate coating, the process controls every variable. Flow meters, torque sensors, load cells, vision cameras, pH probes, temperature controls, and synchronized motors maintain the consistency required for mass production. Every action is automated, but none is simple. The caramel must flow, but not run. The nougat must hold its structure without hardening. Peanuts must fall in even distribution without clumping or rolling. Chocolate must be tempered, coated, shaped, and solidified, without bloom, swirl misalignment, or trapped air. Producing 10 million Reese's peanut butter cups begins with the bulk delivery of core ingredients: roasted peanuts, cocoa liquor, cocoa butter, sugar, salt, milk solids, dextrose, emulsifiers, and stabilizers. Raw materials arrive in tankers, super sacks, and silo containers, and are fed into the production system via automated pneumatic transfers, conveyor augers, or liquid pumps, all connected to centralized control systems that regulate flow, temperature, and mass. The peanut butter core is produced first. Whole roasted peanuts are delivered directly into an industrial-size vibrating hopper. The hopper separates debris, splits, and undersized fragments through a combination of screen grating and air jets. The selected peanuts are passed through a second roasting stage in a continuous rotary drum oven, bringing their internal temperature above 160 degrees C. This ensures uniform oil release and deepens flavor. As they exit the roaster, the peanuts are immediately cooled using a forced air cyclone system to prevent over-roasting. Cooled peanuts are fed into a hammer mill, where rotating steel blades grind them into a fine, warm paste. The paste flows directly into a ribbon blender, where sugar, salt, dextrose, and stabilizers are added. The blender's high shear paddles fold and mix the ingredients, creating a thick, creamy filling with a controlled moisture content and spreadable viscosity. Viscosity sensors and torque meters monitor the blend in real time. The finished peanut butter is pumped into heated jacketed holding tanks equipped with agitators that keep the filling homogeneous and at a stable flow temperature around 45 degrees Celsius. Meanwhile, chocolate production runs in parallel. Cocoa liquor, cocoa butter, sugar, milk solids, and lecithin are fed into a high-capacity conche. The conche kneads and heats the mixture, allowing moisture and acidity to evaporate. Internal temperature is held between 50 °C and 60 °C. Once the flavor has developed and the texture has been refined to a smooth mass, the mixture is transferred to a 5-roll refiner. In the refiner, steel rollers shear the chocolate mass to reduce particle size to below 20 microns. The refined chocolate is then conched again to polish the particle surfaces, improve flow, and enhance melt. From the conche, the liquid chocolate is pumped through heat-maintained stainless lines into tempering units. Tempering machines cycle the chocolate through 3 thermal zones: heating to fully melt all crystals, cooling to encourage stable seed crystal formation, and reheating to melt unstable forms. The result is chocolate with stable beta crystals that produce a glossy finish and crisp snap. Now the forming line is activated. Pre-formed paper cups are dispensed from a magazine feed into indexed molds on a conveyor belt. A depositor head descends over each cup and fills the base with a measured dose of tempered chocolate. This forms the bottom, shell. As the chocolate hits the cup, the molds are vibrated rapidly, forcing the liquid to spread evenly and coat the cup base. The conveyor then carries the partially filled cups through a cooling tunnel that drops the chocolate temperature to around 10 degrees Celsius over several minutes, solidifying the shell and contracting it slightly away from the paper wall. Next, the peanut butter filling is applied. A piston depositor, aligned with the mold indexing system, dispenses a precise slug of peanut butter directly onto the cooled chocolate base. The volume is tightly controlled, typically 10 to 15 grams per cup, depending on size variant. The warm filling spreads slightly on contact, but retains its form due to its balanced fat structure and cooling effect from the base. A brief second cooling tunnel pass stabilizes the core enough to support the top chocolate layer. The top layer of chocolate is deposited last. Another depositor head applies a final pour of tempered chocolate over the peanut butter core. Vibration removes any trapped air and flattens the surface to an even plane. This final deposit seals the core entirely, forming the completed cup. The filled cups now pass through the primary cooling tunnel, a multi-zone chamber that gradually drops the internal temperature of each cup to ensure uniform crystallization. Airflow, humidity, and conveyor speed are precisely tuned. The full cooling cycle lasts around 10 minutes, allowing the chocolate to fully solidify without forming sugar bloom or fat migration marks. As the cups exit the tunnel, they undergo automated inspection. Vision systems scan every unit for fill height, surface uniformity, and alignment within the paper cup. Cups with off-center deposits, cracked surfaces, or exposed peanut butter are automatically rejected by robotic arms or pneumatic gates. Approved cups continue to the wrapping station. A pick-and-place system lifts each cup and transfers it to the wrapping infeed. Wrapping film, pre-printed with branding and registration marks, is cut to size and wrapped tightly around each cup using a twist wrapping mechanism. The ends are pinched and twisted shut by synchronized spinning belts. Wrapping speeds can exceed 1,000 units per minute per line. Wrapped cups are conveyed through a metal detector calibrated for high sensitivity to both ferrous and non-ferrous contaminants. Any package triggering an alert is automatically diverted. Cleared products are grouped into collating lanes. Collators arrange cups into blister trays or multi-packs. A robotic grouping arm aligns sets of cups and loads them into thermoform trays or folding cartons. These cartons are pre-formed in a high-speed erector. Hot melt adhesive is applied to flaps, and cartons are sealed using servo-driven compression plates. Cartons are printed with date codes and batch numbers using thermal inkjet or laser coders. Completed cartons move toward the palletizing area. Robotic palletizers lift cartons using vacuum, grippers or adjustable forks, and stack them onto wooden or plastic pallets in a fixed interlocking pattern. Slip sheets may be added between layers. Each full pallet is conveyed to a stretch wrapper. A rotating arm applies film from bottom to top, binding the load securely for transportation. All stages are governed by programmable logic controllers. Each machine communicates via industrial Ethernet to a centralized control room. SCADA interfaces display real-time production data, including belt speeds, depositor accuracy, wrapping count, rejection rates, temperature profiles, and chocolate viscosity. Ingredient dosing is closed-loop controlled. If sugar concentration drifts in the peanut butter mix, the feeder corrects flow automatically. Chocolate viscosity is monitored using inline rotational viscometers. Fill weights are verified by high-speed load cells. Position sensors and servo motors keep all timing synchronized across multiple parallel lines. Each line is designed for continuous operation. Changeovers are handled with tool-less part swaps and automated cleaning sequences. Clean-in-place systems, wash tanks, pipes, and depositors between shifts. Heated caustic detergent is pumped through all product contact lines, followed by a water rinse and final sanitizing flush. Flow rate, contact time, and return temperature are logged and verified automatically. Producing 10 million peanut butter cups requires multiple synchronized lines running at high throughput. A single high-speed line can produce over 1,200 units per minute. 10 such lines operating in parallel generate 720,000 units per hour. In a continuous run, lasting just under 14 hours, the full batch of 10 million is completed. Each cup is mechanically identical. Same chocolate mass, same peanut butter volume, same shell thickness, same twist wrap tightness. The consistency is achieved through calibrated depositor nozzles, servo-actuated plungers, precision-heated tanks, and closed-loop feedback across every stage of production. Key tolerances are maintained. Chocolate fill weight within plus as 0.5 grams, peanut butter center within plus 1 millimeter of alignment, wrap tension within 2%, seal temperature within plus 1.5 degrees Celsius. Rejects are tracked and analyzed automatically to detect trends before they cause system-wide variation. Temperature is crucial. Chocolate crystallization, peanut butter viscosity, cooling tunnel performance. Every step is sensitive to thermal drift. Thermocouples monitor all zones, from tanks to tunnels. If any zone deviates from range, alarms sound and the affected section is automatically adjusted or stopped. From the peanut grinding to the pallet wrap, the process is fully integrated. There are no idle steps. Syrup mixing, shell forming, core deposition, sealing, cooling, inspection, wrapping, cartoning, and palletizing flow in continuous sequence. There is no manual intervention. Everything moves in rhythm, guided by sensors, actuators, and control algorithms. Producing 10 million M&Ms begins at the granule level. Core ingredients like sugar, cocoa mass, cocoa butter, milk solids, corn syrup, and food-grade colorants are delivered in bulk. Each component is unloaded into stainless steel silos, insulated storage tanks, or vacuum-sealed hoppers. From there, pneumatic conveyors and positive displacement pumps transfer the raw materials into the processing line with exact flow control. Every ingredient is monitored by mass flow meters, auger dosing systems, and load cell integrated vessels to ensure accurate, repeatable input ratios. The first major step is creating the chocolate centers. These are not flat discs to start with. They begin as lentil-shaped chocolate pieces, formed, cooled, and prepared for shell coating. Chocolate production occurs in a multi-step blending and refining system. Liquid cocoa liquor, cocoa butter, and sugar are pumped into a conche. In this high shear mixing chamber, ingredients are heated and agitated over hours, reducing acidity and moisture while developing flavor. The mass then flows into a 5-roll refiner. This machine crushes the chocolate through narrowing steel rollers until particle size falls below 20 microns, producing the creamy texture needed for M&M's centers. The refined chocolate returns to a second stage conche for additional smoothing. From the conche, the chocolate mass is pumped through jacketed pipes into tempering units. These systems rapidly cycle the chocolate through heating, cooling, and controlled reheating phases, encouraging the formation of stable cocoa butter crystals. Tempered chocolate exits at a tightly maintained viscosity and temperature, ready for molding. The molding system produces the core. Individual chocolate lentils are formed by depositing droplets of tempered chocolate onto a chilled belt. As each droplet lands, it spreads slightly before solidifying into the iconic disc shape. High-speed vibratory tables level and settle each piece before the belt enters a rapid cooling tunnel. Cold air circulates above and below to ensure uniform hardening. Each M&M-sized piece is checked by laser sensors for thickness and diameter tolerance. Once solidified, the chocolate cores are collected into stainless steel bins and conveyed to the panning room. Here begins the defining process. Sugar shell coating through precision, layering in automated panning drums. The panning drums are large rotating cylinders with polished stainless interiors. Thousands of chocolate cores are loaded into each drum. As the drums rotate, a fine mist of sugar syrup is sprayed through atomizing nozzles. The syrup is a concentrated mix of sugar, glucose, and water, heated to remain fluid but not overly thin. The chocolate cores tumble while the syrup coats them evenly. Cold, dehumidified air is blown into the drum chamber to dry each layer. This process is repeated across dozens of cycles. Each round adds a thin sugar layer. The rotation angle, drum speed, airflow, syrup volume, and spray pattern are all programmable and adjusted in real time by feedback systems. The cores grow gradually, layer upon layer, until the shell thickness reaches the target range. Throughout the panning process, non-contact sensors monitor shell diameter growth. Cameras detect shape anomalies or cracks. Any defective units are removed automatically using vibration sorters and size classifiers. After achieving the proper shell thickness, the final stage of the sugar coating is the polishing sequence. Polishing begins with a thin application of carnauba wax and food-grade glaze. These are sprayed inside the rotating drum, creating a slick coating on the sugar shells. Buffing arms inside the drum press and polish the surface as it spins, producing the high-gloss finish M&Ms are known for. The shine is not just cosmetic, it also protects the candy shell from humidity and reduces friction during packaging. Now, the finished M&Ms are conveyed into the color coding system. The distinctive red, yellow, blue, green, orange, and brown shells are not coated one at a time. Instead, batches are divided and each drum is designated for a specific color. Colorant solutions, made from water-soluble dyes and a sugar base, are sprayed into the rotating drum in much the same way as the shell syrup, but in smaller quantities. The dyed layers are dried with a gentler airflow to prevent streaking or pooling. After color coding, another pass of polishing glaze is applied for clarity and shine. After drying, M&Ms are released onto vibrating conveyor belts. These belts sort the pieces, prevent sticking, and align them into single-file lanes for printing. A laser-guided inkjet system prints the signature M on each piece. Optical sensors locate the center of each candy and trigger the inkjet nozzle to fire the white food-grade ink at exactly the right spot. The print dries in under 1 second using forced air and low heat. The print tolerance is within 1 millimeter per piece. Any candy without a printed M or with a misprint is identified by high-resolution cameras and removed from the stream. Printed M&Ms pass through a metal detector that scans for ferrous, non-ferrous, and stainless steel contaminants. They then flow into a check weigher, which confirms the average weight of grouped candies matches the package specification. If the weight falls outside a narrow band, that group is rejected. Now the candies are funneled into packaging units. Depending on the format, single-serve pouches, theatre boxes, tubes, or multi-packs, the M&Ms are guided through volumetric fillers, counting systems, or load cell-based dosing mechanisms. For pouches, horizontal form-fill-seal machines draw roll-fed plastic film, print batch codes, and form it into bags. A vertical chute dispenses a fixed volume of M&Ms into each bag, which is then sealed with a heated jaw. For boxed formats, cartons are formed from flat blanks by a mechanical erecting arm. Pre-grouped M&Ms are poured into the boxes using funnel-shaped hoppers with vibratory feeders to ensure consistent flow. Boxes are sealed using hot melt glue and compressed under pressure for final closure. All packages are marked with laser-etched batch codes and expiration dates as they exit the system. Finished packages move on to conveyor belts toward the robotic palletizing area. Here, industrial robots equipped with vacuum pads pick up multiple units at once and stack them in program formations onto wooden pallets. Slip sheets are inserted automatically for stability. Once stacked, the pallet moves to a stretch wrapping unit. A rotating arm applies plastic film tightly around the load to prepare it for distribution. To reach 10 million units, the process relies on multiple parallel lines. Each high-capacity line can produce more than 2,000 pieces per second. With 10 synchronized lines running continuously, the factory generates 72,000 pieces per second. over 4.3 million per minute. In just under 40 minutes, the full 10 million pieces are completed, each one identical in size, shape, coating, gloss, and print. All steps are governed by programmable logic controllers. The entire factory is coordinated through a distributed control system, with real-time SCADA dashboards showing every variable: syrup viscosity, shell thickness, air humidity, shell growth rate, rotation speed, dye concentration, gloss level, printing accuracy, and package weight. Sensors monitor the production line at every point. Shelling drums use load cells to detect overfill. Thermocouples track temperature inside conchis, tanks, and coating units. Flow meters control syrup delivery. Cameras confirm print legibility. Servo motors handle belt timing, robotic arm movement, and package alignment. Cleaning cycles run automatically between batches. Sugar lines, chocolate tanks, conchis, panning drums, and depositor heads are cleaned using hot, circulating detergent, followed by high-pressure rinses. All cleaning steps are validated by chemical conductivity sensors and logged for traceability. The factory layout is linear but modular. Chocolate production, shell coating, coloring, printing, and packaging are linked by buffer zones that allow for surge capacity. If one stage slows, others continue without shutdown. Every section has redundant machinery to allow for changeovers and maintenance. Tolerance ranges are tight. Shell thickness must fall within +0.15 mm. Chocolate center weight must remain within +0.2 grams. Printing alignment cannot vary more than 1 mm. Shell color concentration is monitored by spectrophotometers to ensure consistency across millions of pieces. Every variable, from syrup crystallization to drum angle to print timing, is calibrated for absolute uniformity. This level of precision ensures that 10 million M&Ms are not just mass-produced, but identically produced. Each one carries the same shine, the same crunch, the same chocolate-to-shell ratio, and the same instantly recognizable M. From grinding cocoa to molding chocolate, from layering sugar to polishing glaze, from color batching to robotic stacking, the process never stops. The result is a continuous stream of motion, heat, rotation, and control, where every piece, every shell, and every package flows through the system in perfect mechanical choreography. The production of Cheetos begins not with cheese or seasoning, but with one humble ingredient: corn. In fact, the specific type of corn used in Cheetos manufacturing is carefully selected and processed to meet exacting technical standards before it even enters the plant. The base product of every Cheeto is degermed cornmeal, derived from a variety of field corn that is specially cultivated for its high starch content and low fat levels. This corn must produce a uniform, predictable puff when subjected to extreme heat and pressure, so its density, moisture content, and kernel hardness are closely monitored even at the agricultural stage. Farmers contracted by the manufacturer are required to meet tight tolerances in grain quality, harvesting methods, and post-harvest drying to ensure the raw corn will meet the standards for industrial puffed snack production. Once harvested and transported to the ingredient supplier, the corn undergoes an initial cleaning to remove plant debris, soil, and foreign materials. It is then taken through a degermination process, in which the outer bran layer and the germ, the oil-rich, nutrient-dense part of the corn kernel, are removed. This step is essential. While germ and bran contain healthy fats and proteins, their presence can negatively impact the expansion properties and shelf life of the final product. Germ oil can go rancid over time and interfere with the consistent puff structure that defines a Cheeto. What remains after degermination is the starchy endosperm, milled down into a fine cornmeal that becomes the building block of every puff. This cornmeal is then enriched with a blend of vitamins and minerals, including riboflavin, niacin, iron, and folic acid. The enrichment not only helps meet nutritional labeling requirements, but also contributes to uniformity in the extrusion process, as these additives influence how the mixture reacts under heat and pressure. The resulting product is a dry, golden yellow flour with a specific granulation profile tailored to the plant's extrusion parameters. Before it is used on the production line, the cornmeal is stored in temperature and humidity-controlled silos directly connected to the processing plant. These silos often hold hundreds of metric tons of product and are designed to keep the cornmeal in a stable state for extended periods. Pneumatic systems transfer the cornmeal through stainless steel pipelines to weigh hoppers on the factory floor, where batch sizes are precisely measured. Real-time inventory sensors track the flow of material and communicate with the factory's central control system to automatically replenish supply lines as needed, ensuring uninterrupted production. Now it's time for the first transformation phase, hydration and preconditioning. The cornmeal is metered into a continuous mixing system where it is blended with water or steam to raise its moisture content to a narrowly specified range, usually between 15% and 20%. This step is essential to prepare the starch molecules for gelatinization. The equipment used here is not unlike a ribbon blender or paddle mixer, which agitates the mixture thoroughly to ensure every granule of cornmeal is evenly hydrated. Water is introduced through atomizing nozzles positioned at calculated intervals along the mixer's length, and multiple moisture sensors along the pathway feed back to the PLC system to adjust water input in real time. This moist mixture, often referred to as dough, despite its loose, crumbly texture, is held briefly in a conditioning tank to allow for even moisture distribution. The temperature and residence time are carefully controlled. If the mix is too hot or too wet, it may pre-gelatinize and clog the extruder. Too dry, and it won't expand properly. During this stage, the product is slowly moved along a jacketed screw conveyor that maintains a consistent temperature and prevents clumping. Now we arrive at the heart of the production line, the extruder. Industrial Cheetos are made using a twin screw extruder, one of the most sophisticated and critical machines in the plant. The twin screw configuration allows for highly controlled processing of the corn mixture, providing better mixing, higher shear, and superior control over temperature and pressure compared to single screw models. The hydrated cornmeal is fed into the extruder barrel, where it encounters two rotating screws that convey the material forward under intense mechanical pressure. External heaters line the barrel and raise the temperature incrementally as the product moves through each zone. Inside, shear forces generated by the screws convert some of this mechanical energy into heat, further increasing the temperature of the dough. The intense conditions inside the extruder, pressure in the range of 200 to 500 psi, and temperatures from 130 degrees Celsius to 180 degrees Celsius, cause the starches in the cornmeal to gelatinize and the water to superheat. The dough undergoes plasticization, becoming a molten mass under pressure. As this molten dough reaches the end of the barrel, it is forced through a die, the precision-crafted metal plate that defines the shape of the puff. The die hole is round and small, but as the dough exits into atmospheric pressure, the superheated water in the mixture flashes into steam, causing the structure to puff and expand dramatically in a fraction of a second. This rapid expansion is responsible for the iconic airy texture of a Cheeto. Just outside the die, rotating knives spin at high speed, slicing the continuous stream of puff into uniformly sized segments. The speed of the knives determines the length of the puff, while the pressure and temperature within the extruder affect its diameter and density. But even after this high-tech transformation, the newly extruded Cheetos are far from finished. They are still pale, moist, and bland, essentially unseasoned corn puffs. The next stage is all about turning them into the crunchy, craveable snack that consumers instantly recognize. First, the extruded pieces are conveyed via vibrating trays to a frying system. Here, they're submerged in hot oil, typically corn or canola oil, at carefully controlled temperatures ranging between 160 degrees Celsius and 180 degrees Celsius. The residence time in the fryer is only about 20 to 40 seconds, but in that time, the moisture content is reduced dramatically from around 15% to under 2%. This not only creates the final crispy texture, but also deepens the color slightly, giving the snack its characteristic golden hue. The fryer itself is a marvel of engineering, equipped with multiple sensors and filtration systems. Oil turnover rates are high, meaning that fresh oil is constantly added, while spent oil is removed and filtered to maintain quality. Skimmers remove any floating particles, and oil chemistry is monitored for signs of oxidation, free fatty acid levels, and polymerization. If any readings fall outside of the strict parameters, the fryer automatically triggers corrective actions, dosing with fresh oil, increasing filtration, or even pausing the line to prevent compromised batches from continuing downstream. After exiting the fryer, the Cheetos are carried on mesh conveyors through an air cooling tunnel. High-powered fans blow ambient or conditioned air over the freshly fried snacks, bringing them to a safe handling temperature and ensuring any surface oil solidifies just slightly to help the seasoning adhere. These cooling conveyors are extended and designed with soft vibratory motion to prevent breakage, ensuring that the delicate puffs remain intact before entering the seasoning phase. Next, the Cheetos are transferred into a massive rotating flavor drum, where their bland exterior is transformed by a shower of powdered cheese blend. But before we dive into the complexities of seasoning, we'll need to explore how oil coating is applied for adhesion and how powder distribution systems are calibrated to ensure every single puff gets the perfect amount of flavoring. This next part of the production process is where precision meets sensory science, and the result is the addictively cheesy snack that has become a global favorite. Now it's time to dive into one of the most iconic and intricate stages in Cheetos manufacturing, the flavoring phase. This is where the bland, puffed, and fried corn kernels are transformed into the intensely savory, cheese-coated snacks recognized all over the world. The process of seasoning Cheetos is not merely about tossing on a bit of cheese powder. It is an engineered, tightly controlled operation that determines product consistency, taste balance, visual appeal, and even mouthfeel. Everything from the size and porosity of the puff to the electrostatic charge of the powder particles is taken into account in this phase. After exiting the cooling conveyor from the fryer, the puffs are transferred into large rotating cylindrical drums called flavor tumblers. These drums are typically positioned on a gentle incline and rotate slowly, creating a continuous cascade of puffs inside the drum that exposes every surface area of each piece as they tumble forward. This mechanical tumbling is crucial. It ensures an even coating without crushing the fragile, aerated product. Inside the drum, two key applications occur almost simultaneously. First, a fine mist of oil is sprayed onto the hot puffs. Then, a controlled stream of seasoning powder is dispensed over the tumbling mass. The oil, which is typically a neutral vegetable oil like corn or canola, plays several roles in this step. Primarily, it acts as an adhesive layer that allows the seasoning powder to stick effectively to the puff's surface. Additionally, it helps activate the flavor compounds in the powder blend, carrying volatile aroma molecules and enhancing taste perception. The oil spray system uses ultra-fine atomizing nozzles that are precisely calibrated to deliver a uniform coat without oversaturation. Too much oil, and the puffs become greasy and soggy. Too little, and the powder won't adhere properly, leading to uneven seasoning distribution and flavorless bites. The timing, angle, and rate of oil application are closely monitored and adjusted by sensors and programmable logic controllers. Real-time feedback systems measure oil usage, droplet size, and the thermal signature of the puffs to ensure that coating is optimal under varying production speeds or ambient conditions. This level of automation ensures consistency across thousands of pounds of product produced per hour. As the puffs are coated in oil, the seasoning powder is introduced using a vibratory feeder or screw conveyor system. The powder is held in a hopper mounted above the flavor drum and is dispensed through controlled openings at a fixed rate, matched to the flow of puffs. The exact dosing rate depends on the type of Cheetos being produced. Flamin' Hot varieties require slightly more powder per unit than the traditional cheese puffs due to differences in density, powder, granularity, and flavor intensity. The seasoning blend itself is a complex formulation engineered not only for taste, but also for flow characteristics, adhesion, and shelf stability. The base of the powder is often dehydrated cheddar cheese, spray-dried into a fine particle form. This is combined with whey or whey protein concentrate, maltodextrin, salt, monosodium glutamate, MSG, disodium phosphate, citric acid, and natural or artificial flavors. Each of these ingredients plays a very specific role. Maltodextrin, for example, acts as a carrier and anti-caking agent that helps the powder distribute evenly and resist clumping. Citric acid provides a tangy bite that enhances cheese flavor. MSG boosts umami and deepens savory perception. Color additives like annatto or oleoresin paprika for classic cheese, and red 40 or yellow 6 for Flamin' Hot are oil dispersible pigments that give the snack its vivid appearance without creating spotting or streaks. The particle size distribution of the powder is engineered to align with the surface texture of the puffed snack. Powder that's too coarse will fall off, and powder that's too fine will clump or create an overly dusty texture. To prevent powder fallout, electrostatic systems are sometimes used in high-speed lines. In these cases, the powder is given a minor static charge to improve its affinity for the puff surface, minimizing waste and improving adhesion. Inside the flavor tumbler, the balance of oil spray and powder distribution creates a beautiful, uniform layer of seasoning that fully coats each puff without pooling at the bottom of the drum or leaving bald spots on the product. The drum's internal design is key. Angled baffles gently lift and drop the puffs to keep them moving without subjecting them to mechanical stress. As the snacks make their way to the end of the drum, they are now visually and sensorially transformed. Bright orange, evenly coated, and bursting with aroma. Once the seasoning phase is complete, the fully flavored Cheetos are gently transitioned to the final conveyor belt systems that lead to the packaging area. Here, another series of quality control measures come into play. Inline camera systems inspect color uniformity and powder coverage using advanced image recognition algorithms. If a section of the product stream is detected to have an irregular appearance, whether due to light seasoning, overcoating, or discoloration, it is flagged and diverted from the main line for manual inspection or disposal. At this point, the Cheetos are still vulnerable to moisture pickup, oxidation, and mechanical damage, so the packaging process must move swiftly and with precision. The conveyor system delivers the finished puffs to a multi-head weigher mounted above the bagging machines. This machine uses multiple weigh hoppers to rapidly measure exact product portions, typically in the range of 28 g to 250 g per serving, depending on the bag size. These weighers use real-time load cell feedback to select the optimal combination of buckets to match the target weight, within a tolerance as tight as +2G. Each pre-measured portion is released down a chute into a vertical form-fill seal (VFFS) machine. These machines work by pulling a flat roll of pre-printed film through a collar that forms it into a tube. The bottom of the tube is heat sealed to create the first seam, the Cheetos are dropped in, and then the top is sealed and cut, simultaneously forming the bottom seal of the next bag in line. These machines can fill and seal over 100 bags per minute per lane, and multiple lanes often run in parallel for large-scale production. The film used for the packaging is multi-layered and engineered to provide barrier protection against light, oxygen, and moisture. It typically includes an outer polyester film for print quality and visual appeal, a middle layer of aluminum or metallized polypropylene for oxygen and light resistance, and an inner polyethylene layer for heat sealing and moisture resistance. As each bag is sealed, a date code, batch number, and factory identifier are printed using high-speed inkjet printers for traceability. Just after sealing, every bag passes through a series of checkpoints. Metal detectors scan for any foreign objects, vision systems verify print alignment and code readability, and weight checkers ensure compliance with regulatory standards. Non-conforming bags are automatically ejected onto a rejection conveyor, where they are set aside for manual inspection. Approved bags are then grouped and packed into cardboard shipping cartons by robotic pick-and-place systems or automated drop packers. These cartons are sealed, barcoded, and routed to the palletizing station. Here, industrial robotic arms stack the cartons onto wooden or plastic pallets using optimized patterns for stability and load balance. As each pallet is completed, it is wrapped in stretch film to secure the load and protect it from dust and humidity during storage and transportation. The palletized loads are then scanned into the plant's warehouse management system, which tracks location, batch status, and distribution destination. Some pallets are moved to ambient storage if they are designated for short-haul routes, while others are transported to climate-controlled storage areas that maintain low humidity and consistent temperatures, ensuring that the product maintains its texture and flavor until it reaches its final destination. What follows is the outbound logistics phase, where the pallets are loaded onto trucks, routed to distribution centers, and delivered to retailers. But for now, every step inside the production facility, from the moment the cornmeal is hydrated to the final bag, passing the last inspection point, has been a meticulously engineered series of chemical, mechanical, and sensory transformations. Every component of the Cheetos production line is designed not just for efficiency and speed, but to deliver a reliably indulgent experience in every bag. And it all happens in a continuous, automated, high-output environment that must maintain exacting standards of quality, cleanliness, and consistency hour after hour, shift after shift. One of the key operational pillars at this stage is environmental control. Temperature, humidity, and airflow within the production zones are tightly monitored and controlled around the clock. Cheetos, especially after frying and seasoning, are highly sensitive to ambient conditions. If the air in the seasoning or packaging area carries too much humidity, for instance, the cheese powder may begin to clump, reducing its dispersibility and leading to uneven coating. Worse still, excess moisture can cause the puffs to begin absorbing water from the air, softening the texture and compromising the crisp, dry bite expected by consumers. To prevent these issues, HVAC systems specifically engineered for food processing environments are deployed throughout the Cheetos plant. These systems do more than just heat or cool. They dehumidify, filter, and exchange the air in sensitive zones at rapid intervals, ensuring a constant flow of purified, dry, temperature-stabilized air. Some areas, such as the seasoning tumblers or the vertical form-fill seal zone, may be isolated with positive air pressure to ensure that external air, dust, and contaminants do not seep into these critical zones. These environmental systems are integrated with digital controls that feed data into the facility's central monitoring hub. Temperature and humidity data are tracked every few seconds, and if any reading moves outside of pre-programmed tolerances, automatic alarms notify technicians to investigate immediately. In some cases, the system will even halt upstream processes automatically to prevent production under unsuitable conditions, protecting product quality. While environmental controls maintain external conditions, another system ensures the quality of what's happening on the line. Inline quality assurance and real-time analytics. Throughout the Cheetos line, from extrusion to bagging, dozens of sensors, scanners, and cameras work in unison to gather data on key quality metrics. These include moisture content, oil absorption rate, puff size, color uniformity, seasoning coverage, and weight per unit. Each of these factors contributes not only to taste and mouthfeel, but to customer satisfaction and regulatory compliance. Advanced laser micrometers and stereo imaging cameras measure the dimensions of each puff as it moves across the line at high speed. If puffs fall outside the programmed size range, either due to inconsistent extrusion pressure, die blockage, or improper cutting, those units are flagged and rejected automatically using pneumatic diverting arms. Simultaneously, optical sensors inspect the color of the fried puff to confirm it matches brand-specific targets. Color variation could indicate improper frying time, fluctuating oil temperature, or oil degradation. The system will trigger alerts or shut down sections of the line if it detects drift from acceptable limits. Another important part of inline quality is the metal detection system. Every snack must pass through high-sensitivity metal detectors or, in some cases, X-ray systems just before packaging. These devices scan for trace amounts of ferrous, non-ferrous, and stainless steel contaminants which could originate from worn machinery parts, upstream, or during maintenance. The sensitivity of these machines is such that they can detect metallic particles smaller than a millimeter in diameter. If a contaminated bag is identified, it is automatically ejected from the line, recorded in a digital log, and sent for root cause analysis. In high-output snack manufacturing, product changeovers are another critical concern. A single plant might produce multiple Cheetos variants: classic cheese, flamin' hot, jalapeno cheddar, and limited editions on the same line, sometimes switching several times per day. To avoid cross-contamination of flavor profiles and allergens, the factory must execute a full product changeover, which includes both physical and procedural steps. The final bags of one variant are run through the line until the seasoning and product types are completely cleared. Following that, dry cleaning and wipe down protocols are enacted on exposed surfaces. In flavor tumbler zones and powder feeding systems, residue removal is handled by a combination of mechanical vacuums, compressed air nozzles, and in some cases, wet cleaning cycles. Pipes carrying seasoning powder are often disassembled and cleaned manually or flushed with air-driven pigs, foam or rubber projectiles that scrape the interior of the tube clean as they are propelled by compressed air. All cleaning steps are verified through ATP, adenosine triphosphate, swab tests, or allergen-specific strip tests to confirm the line is ready for the next product. Equipment cleaning and sanitization extend far beyond changeovers. Each section of the production line is scheduled for deep cleaning on a regular basis, with some components cleaned daily, others weekly, and critical systems, like oil fryers, undergoing monthly shutdowns for intensive maintenance. Every cleaning task is documented in a digital sanitation log that includes time-stamped photos, chemical usage records, technician ID, and verification by a supervisor. This log ensures compliance with food safety regulations and internal auditing systems. Speaking of oil fryers, one of the more maintenance-intensive systems in the Cheetos plant is the oil management setup. Used frying oil is constantly cycled through multi-stage filtration systems that remove fine particulates and oxidized residues. Inline sensors monitor oil color, free fatty acid content, and total polar compounds, all indicators of oil degradation. When thresholds are approached, fresh oil is introduced, and a portion of the old oil is purged to waste recovery tanks. This spent oil is not discarded haphazardly. Instead, it is captured and sent to third-party processors who refine it for use in biodiesel production or industrial lubricants, creating a closed-loop waste management process that supports sustainability goals. Seasoning systems have their own challenges in terms of dust and waste control. Cheese powder and spice blends are notoriously airborne, so extraction hoods fitted with HEPA filters are positioned above tumblers and conveyors to capture stray particles. These systems not only keep the air clean for workers, but also prevent buildup on surfaces and reduce cross-contamination risk. Powder recovered in this way is not reused in production, but is collected and weighed for waste tracking. Many factories monitor seasoning powder yield versus usage to optimize application and reduce excess without compromising flavor intensity. Additionally, factories employ floor-level waste segregation systems, where organic waste, such as broken puffs or overcooked batches, is separated from packaging materials and cleaning byproducts. Organic snack waste is often sent to animal feed processing plants or used in anaerobic digesters to generate energy, while plastics are compacted and shipped to recycling partners. These systems not only reduce landfill usage, but also lower the facility's total environmental impact per unit of product. Every phase of the factory's operation is governed by a robust system of documentation and auditing. Real-time production data is logged into the Manufacturing Execution System, MES, which connects to the plant's Enterprise Resource Planning, ERP, platform. This system allows plant managers to track every batch of Cheetos from cornmeal input to palletized output. If a quality issue is flagged post-distribution, every input, cornmeal batch, oil lot, seasoning blend, even the operator ID can be traced within seconds. This level of transparency is essential for large brands that operate under continuous scrutiny from regulators, retailers, and consumers alike. All these systems, from the air handlers and fryers to the conveyors and flavor blenders, are monitored by a central control room staffed by trained process engineers and operators. The control room acts as the nerve center of the factory. Touchscreen interfaces display real-time data on line performance, yield percentages, waste figures, and energy usage. Alarms and alerts notify the team of any deviation in pressure, temperature, fill levels, or machine health. The staff can make remote adjustments, schedule maintenance tasks, and even initiate partial or full shutdowns directly from their stations. In many facilities, predictive analytics platforms are integrated into these systems. Using machine learning algorithms, these platforms analyze historical and current data to forecast when a component might fail, how yield might shift under ambient changes, or what impact a change in oil temperature might have on puff expansion. This allows for proactive decision-making, reducing downtime and maximizing efficiency. The industrial production of condensed milk begins with the careful reception and preparation of raw cow's milk, a phase that determines the quality, efficiency, and final yield of the entire operation. As raw milk arrives at the condensed milk manufacturing facility, typically transported in insulated stainless steel tankers from contracted dairy farms, the first priority is immediate and rigorous quality assessment. Each truckload contains tens of thousands of liters of milk, and every batch must be verified to meet precise industrial standards before being accepted into the plant's supply chain. This initial phase involves a set of standardized protocols carried out in a dedicated receiving bay, equipped with specialized sampling and testing equipment. Upon arrival, the truck is docked to an unloading station, where automated lines connect directly to the tanker's valve. Before unloading can commence, operators perform a series of tests on a representative sample extracted from the tanker. This is done using a sanitized dipper or through a sample port using aseptic techniques to avoid contamination. The sample is then transferred to the plant's on-site quality control lab. Inside this lab, technicians first conduct a sensory inspection, evaluating the milk's color, smell, and presence of any visible particulates. While this step is basic, it's essential in immediately identifying any batches with gross spoilage or foreign contamination. The next series of tests are chemical and microbiological. A cryoscope is used to determine the freezing point of the milk, which helps identify dilution with water. Industrial condensed milk relies on unadulterated raw milk with tightly controlled fat and solids not fat contents. Any dilution affects the solids concentration required for the evaporation phase later on. Following this, infrared spectroscopy or mid-infrared analyzers are used to determine precise fat, protein, and lactose levels. These readings are compared against production targets, usually 3.5 to 4.0% fat and 8.5 to 9.0% SNF. If any component falls out of range, the milk may be either rejected or diverted to other dairy product lines. Another critical check is for microbial load. A rapid plate count or ATP bioluminescence test evaluates the total bacterial count per milliliter. Condensed milk production cannot start with high bacterial loads, as the concentration process would also concentrate any microbial byproducts, leading to off flavors and safety risks. Acceptable raw milk generally must have fewer than 100,000 colony-forming units per ml, with many plants enforcing even tighter limits. Additionally, presence of pathogens such as Listeria or Salmonella are monitored using immunoassay kits or PCR-based rapid tests. Antibiotic residue testing is also performed using either SNAP tests or microbial inhibition assays, since antibiotic contamination can disrupt the fermentation steps used in other dairy operations and might violate export regulations. If the sample passes all tests, the milk is cleared for unloading. The truck's contents are then pumped via sanitary stainless steel pipelines into raw milk holding tanks located within a temperature-controlled section of the facility. These tanks, typically ranging from 20,000 to 50,000 litres in capacity, are jacketed and agitated to maintain a constant temperature of around 4 degrees Celsius. At this stage, the milk is still unpasteurized and considered perishable, so time and temperature control are critical. The tanks are equipped with inline thermometers and CIP spray balls that will sanitize the internal surfaces between batches to prevent cross-contamination. The next step in the process is milk clarification and standardization. This is a pivotal moment where physical impurities and excess variability in composition are removed. The raw milk is fed from the storage tanks to a centrifugal clarifier, a high-speed rotating bowl separator that uses the density differences between milk solids and liquid to remove somatic cells, dirt, and other non-milk particles. The milk enters the spinning drum through a feed pipe, and under centrifugal force, heavier particles are flung outward against the bowl walls and discharged intermittently via sludge ejection ports. After clarification, the milk is sent to a cream separator. This piece of equipment operates similarly to the clarifier, but focuses on removing and isolating the cream layer from the skim milk portion. Depending on the desired end product specifications, some or all of the separated cream may be blended back in. This is where the standardization process comes into play. Condensed milk requires a tightly defined balance between fat content and total milk solids. Operators adjust this balance using inline blending systems, automated control loops equipped with flow meters and density sensors. The goal is to create a uniform milk base, typically around 8.5% fat and 22% total solids before it proceeds to pasteurization and evaporation. Any deviation at this stage would affect the efficiency of the next stages and could compromise the desired thickness, sweetness, and shelf life of the condensed milk. In more advanced factories, these composition adjustments are performed entirely by automated PLC systems. These use real-time data collected from inline sensors to control proportioning valves and regulate the mixing of cream and skim milk streams without any manual input. This level of automation not only ensures consistency, but reduces waste and energy use. The standardized milk is now homogeneous in composition, free of debris, and ready for thermal treatment. Before entering the pasteurizer, it may pass through a deaerator, a vacuum chamber that removes entrapped gases such as oxygen and carbon dioxide, which, if left in, could promote oxidation of fats and off flavors during storage. But up next is a step that changes the physical properties of the milk at a fundamental level. With the raw milk now cleaned, standardized, and compositionally balanced, it's time for it to undergo pasteurization and heat treatment, a step that prepares it for concentration without microbial risk or protein denaturation. This phase involves an intricate dance between temperature, pressure, and time, and it sets the stage for the transformative evaporation process that gives condensed milk its name. Now that the raw milk has been thoroughly received, clarified, and compositionally standardized, it is ready for thermal treatment. The next phase in the factory process is pasteurization, which is critical in destroying any pathogenic or spoilage microorganisms present in the milk. Pasteurization must be done with precise timing and temperature control to ensure microbial inactivation without damaging the milk's nutritional or functional properties, especially since this milk will soon undergo evaporation, which puts it under further thermal stress. To carry this out, the milk is directed from the holding tanks into a continuous flow, high-temperature, short-time pasteurization unit, which is the standard in industrial dairy processing. The HTST system typically consists of a series of plate heat exchangers that are engineered to raise the milk temperature to approximately 85 degrees Celsius for 15 to 20 seconds. This is hotter and slightly longer than conventional drinking milk pasteurization, as condensed milk requires greater microbial stability due to its extended shelf life. The process begins in the regeneration section of the plate heat exchanger, where incoming cold raw milk is preheated by outgoing pasteurized milk, allowing energy recovery and efficiency gains of up to 90%. The milk then moves through the heating section, where it is brought to the target temperature using hot water or steam circulated on the opposite side of the stainless steel plates. The timing of exposure is controlled by the flow rate and volume of the holding tubes, ensuring that every particle of milk receives uniform treatment. After pasteurization, the milk passes into a holding cell monitored by thermocouples and flow diversion valves. If the milk fails to reach or maintain the required pasteurization conditions, it is automatically diverted back to the raw milk tank for reprocessing. Once verified, the pasteurized milk is cooled again in the regeneration section, where it gives off its heat to the incoming raw milk, and then further chilled to around 60 degrees Celsius in preparation for the next crucial step, evaporation. Before entering the evaporator, the milk passes through a balance tank that helps maintain a constant feed rate into the evaporation system, stabilizing flow and avoiding temperature fluctuations that could cause burn-on or fouling inside the evaporator tubes. Now it's time to go into the evaporation stage, which is arguably the heart of the condensed milk production process. This is where the milk is physically transformed, thickened into a rich, viscous product through the removal of water. The goal here is to reduce the water content from its original 87% down to around 60%, achieving a final concentration of about 28% milk solids and 44% added sugar in the case of sweetened condensed milk. This is achieved through multi-effect vacuum evaporation, an energy-efficient process that allows for large-scale water removal without subjecting the milk to damaging high temperatures. The milk enters a multiple effect falling film evaporator, which is the industry standard for large volume dairy processing. In this system, the pasteurized milk is introduced at the top of vertical stainless steel tubes where it forms a thin film as it flows downward. Simultaneously, steam is injected into adjacent chambers that surround the tubes, heating them indirectly. Because the evaporator is operated under vacuum, often at pressures around 70 to 100 millibar, the boiling point of the milk is reduced to around 55 degrees Celsius. This protects the sensitive proteins, sugars, and fats from heat-induced damage, preserving both flavor and nutritional quality. In a multi-effect setup, the vapor produced from one stage is used to heat the next stage, drastically improving energy efficiency. A typical 5-effect evaporator can remove over 85% of the water from milk with minimal energy input, thanks to this cascading reuse of thermal energy. The evaporated water is condensed and collected as waste heat condensate, which can later be recycled within the plant for cleaning processes or steam generation. Inside the evaporator, the thin film of milk continuously loses moisture as it falls. The combination of short residence time, low boiling point, and efficient heat transfer ensures that concentration occurs evenly and rapidly. By the time the milk reaches the bottom of the final effect, it has reached a viscous, concentrated state with a solid content of around 45%. At this point, it is discharged into an intermediate concentrate tank, where it is gently agitated and kept warm to prevent crystallization or skin formation on the surface. But the evaporation process alone does not fully define condensed milk as we know it, especially in the case of sweetened condensed milk. Once the desired solids concentration is achieved, the next critical step is the addition of sugar, which is not merely for taste, but serves as a functional preservative. The high sugar content lowers the water activity of the product to a point where microbial growth is virtually halted, granting it a long shelf life without refrigeration. The method of sugar addition must be extremely precise, as the wrong concentration can lead to issues like crystallization, viscosity problems, or even fermentation in rare cases. To do this, refined white sugar, typically sucrose, is added to the concentrated milk in the form of a hot sugar syrup. This syrup is prepared separately in jacketed mixing vessels, where dry granulated sugar is dissolved in water and heated to around 70 degrees Celsius. The syrup is filtered to remove any particulate matter and pumped into the concentrate tank under controlled flow rates. The typical formulation is around 46% sucrose by weight in the final product, which is determined by a combination of inline refractometers and density meters. The mixing of sugar syrup into the concentrate must be uniform to prevent localized crystallization and is often aided by low shear agitators that maintain homogeneity without introducing air. As the sugar is added, the milk becomes even more viscous and dense. At this point, the product's temperature is carefully maintained between 60 degrees Celsius and 65 degrees Celsius, as dropping below this range can initiate premature crystallization, while higher temperatures can scorch the milk solids. Once the sugar is fully integrated, the mixture is briefly held in a jacketed holding tank for a process known as equilibration, which allows any remaining air bubbles to rise and dissipate and gives time for the solution to reach equilibrium in terms of water activity and solute concentration. This marks the end of the thermal and compositional transformation stages. From a microbiological and physicochemical standpoint, the product is now shelf-stable, viscous, and chemically preserved by both heat treatment and high sugar concentration. However, it's not yet ready for packaging. There are still important steps to take involving cooling, crystallization control, and downstream finishing that are vital to achieving the smooth texture and glossy appearance that define high-quality condensed milk. With the concentrated sweetened milk now fully blended and equilibrated, the next critical phase in the condensed milk manufacturing process is controlled cooling and crystallization. This step is vital not only to achieving the desired texture and viscosity, but also to ensuring long-term product stability. If cooling is done too quickly or without proper control over nucleation, the lactose and sucrose in the product can crystallize into large, gritty particles. This not only affects mouthfeel, but can also lead to phase separation over time. To avoid this, the condensed milk is sent through a carefully engineered cooling and seeding system that promotes the formation of microcrystals, small, evenly distributed sugar crystals that give condensed milk its signature, smooth, glossy consistency. The cooling system typically consists of scraped surface heat exchangers or jacketed tubular coolers. These systems are designed to handle highly viscous liquids and provide a high degree of thermal control. In scraped surface heat exchangers, the condensed milk flows through a cylindrical barrel while rotating blades constantly scrape the inner surface. This ensures that no product burns or sticks to the hot surface, and that the entire volume of milk is uniformly cooled. The cooling medium, usually chilled glycol or water, is circulated through the jacket, gradually lowering the milk temperature from around 65 degrees Celsius to 30-35 degrees Celsius. As the milk cools, it passes through a crystallization chamber where it is inoculated with fine lactose or sucrose seed crystals. These seed crystals are introduced in a controlled manner using a dosing system that meters out microscopic crystals with a high surface area. The goal is to initiate crystallization at a molecular level, encouraging the dissolved sugars to form consistent and extremely fine crystals rather than large, coarse ones. Agitators in the crystallization chamber are designed to promote gentle but thorough mixing, ensuring uniform distribution of the seed material without incorporating excess air, which could lead to oxidation or microbial contamination. Once seeded, the mixture is held at a stable crystallization temperature, typically around 30 degrees Celsius, for a period ranging from 30 to 90 minutes, depending on the batch size and product formulation. This resting period allows the crystals to grow slightly while remaining small and suspended, forming a delicate lattice within the viscous matrix of the milk. It is during this stage that the final texture of the condensed milk is locked in. Operators closely monitor the product's Brix value, viscosity, and temperature, using inline sensors and laboratory sampling to ensure that the crystallization proceeds according to specification. After the crystallization phase, the product enters the deaeration stage. Despite all precautions taken during processing, the condensed milk will inevitably contain some entrapped air, either from mechanical mixing, seeding, or agitation. This air must be removed before packaging to prevent oxidation, which can degrade both flavor and color over time. Deaeration also helps improve fill accuracy during packaging, ensuring a stable and uniform product weight in each container. Deaeration is typically carried out in a vacuum deaerator tank. The condensed milk is pumped into the tank, which is maintained under a vacuum of around -0.8 bars. Inside the tank, the milk is spread into a thin film across a series of rotating trays or falling film surfaces, maximizing the exposed surface area. As the product spreads out under vacuum, dissolved gases and trapped air are released and drawn out by the vacuum pump system. In some systems, nitrogen gas is also bubbled through the product as a stripping agent to help displace oxygen more effectively. This process is continuously monitored with oxygen sensors to ensure minimal residual oxygen levels in the final product, typically less than 0.5 milligrams per liter. Once deaerated, the condensed milk is often passed through a final homogenization stage. While not strictly required in all formulations, homogenization is frequently used to improve product consistency, prevent fat separation, and extend shelf stability. In this process, the milk is forced through a narrow orifice under high pressure, usually between 100 to 150 bar, causing the fat globules to break down into much smaller sizes, typically less than 1 micron in diameter. This prevents creaming or separation during storage and gives the final product a more uniform mouthfeel. The homogenizer used in this step is typically a two-stage piston-type homogenizer. In the first stage, pressure is applied to break apart the fat globules. In the second stage, the product is passed through an impact ring to further disperse and stabilize the emulsion. This ensures that the fat remains evenly distributed throughout the viscous condensed milk matrix, even after months of storage on a shelf. The process must be carefully balanced to avoid over-shearing the product, which could break the sugar crystal structure and lead to syneresis or texture issues. With the product now fully processed, it moves to the packaging line. Before any milk enters a can or a tube, the packaging material itself must undergo preparation. Metal cans are the most common format for condensed milk, though plastic tubes and laminated pouches are also used depending on market demands. The cans arrive at the factory either as pre-formed containers or as rolled flat blanks that are formed and sealed on site using can-forming machinery. If using pre-formed cans, the first step is depalletizing and feeding. The cans are automatically unloaded from shipping pallets and fed into a cleaning system via conveyor belts. Here, they pass through a high-pressure air blower system that removes dust and debris. They may also pass through an inverted rinse tunnel that sprays them with sterile water or a mild sanitizing solution. Optical sensors verify that each can is intact and free of damage before it proceeds. The clean cans are then transported to the filling station, where they are indexed into position beneath nozzles connected to a positive displacement filler system. These filling machines are designed to handle thick, viscous liquids with high precision. A typical condensed milk filling machine includes a volumetric dosing mechanism that ensures every can receives the exact same quantity, usually around 397 grams, the standard retail size. Sensors ensure the nozzles do not drip or splash, and the filling process is conducted in a low oxygen environment to prevent post-process contamination. As cans are filled, they immediately move to the vacuum closing station. This is another critical step in ensuring product longevity. Before the lid is sealed, a vacuum is applied to the headspace in the can to remove residual air. This helps prevent oxidation and maintains the slight negative pressure required for a tight seal. The lid is then applied and hermetically sealed using a double seam seaming machine. This creates an airtight seal by mechanically folding and compressing the lid and can flange together in two operations. The quality of this seal is checked automatically using seam gauges and vision inspection systems to detect any defects or incomplete closures. After sealing, the cans enter a hot water bath or steam chamber for thermal holding. This step, known as in-can sterilization or thermal stabilization, involves heating the sealed cans to around 85 to 90 degrees Celsius for 15 to 20 minutes. This serves several functions. It neutralizes any residual microbes that may have entered during filling, helps equalize pressure inside the can, and further reduces the water activity of the product. The heating process is tightly controlled using a time temperature data logger to ensure consistency across batches. Once the thermal holding is complete, the cans are rapidly cooled using chilled water sprays or immersion tunnels. This quick cooling halts the cooking process and helps set the product structure inside the can. It also prevents over-darkening, which can occur due to Maillard reactions between milk proteins and sugars at elevated temperatures. The cans are then dried using air knives and conveyed to the labeling and coding area. Each can is now labeled with full product information, including nutritional facts, production batch codes, expiration dates, and allergen warnings. Laser coders or inkjet printers apply traceability codes directly onto the lid or bottom of each can, allowing for full tracking throughout the supply chain. These codes are critical for food safety as they allow for rapid recall or identification of affected batches in the rare event of a contamination issue. From here, the cans are packed into cartons or shrink-wrapped into bundles using automated case packers. The cartons are stacked onto pallets and wrapped with stretch film for transport. At this stage, finished condensed milk is subjected to final quality inspection, where random samples from each batch are tested for Brix value, fat content, microbial load, viscosity, and packaging integrity. Once the batch is cleared, it is released for distribution. With the cans now fully sealed, labeled, and palletized, the condensed milk moves into the final stretch of its industrial journey: post-production storage, distribution, and market readiness. While it may seem that the heavy lifting is over, these concluding steps are far more complex and technologically managed than they first appear. Factories invest significant resources to ensure that every can of condensed milk not only leaves the facility in perfect condition, but also maintains its quality throughout the entire shelf life, often up to 2 years or more. Immediately after packaging, pallets of condensed milk are transferred to temperature-controlled finished goods warehouses. The climate in these storage areas is tightly regulated, typically kept between 15 degrees Celsius and 25 degrees Celsius, with relative humidity under 60%. This environment prevents moisture accumulation on the can surfaces and limits the rate of any chemical reactions inside the product, such as non-enzymatic browning. Even though the condensed milk is shelf-stable, excessive heat over time can darken the color and subtly change the flavor profile. These storage conditions are monitored 24/7 using IoT-connected environmental sensors that send real-time data to the facility's central control system. Each pallet is barcoded with batch numbers and entered into a digital warehouse management system. This system not only tracks location and inventory levels, but also enforces FIFO protocols to ensure older batches are distributed before newer ones. The traceability codes printed earlier on the cans come into play again here. Every single unit can be traced back to its raw milk intake, processing parameters, operator ID, and time-stamped process logs. This full chain traceability is a critical part of modern food safety compliance. When orders are received from retailers, exporters, or institutional buyers, automated robotic pallet pickers retrieve the relevant stock and move it to the outbound shipping area. Here, it is loaded into refrigerated or insulated trucks, depending on the destination and regional climatic conditions. In many cases, international shipments involve placing pallets into reefer containers that maintain stable temperatures for transoceanic shipping routes. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses: never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean to fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada, primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3 ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers, often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture, which allows it to hold up through the unique double frying process that Five Guys uses in-store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched, and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than +1 g. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun's structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use-by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated. Five Guys moves thousands of pounds of beef and buns through a supply chain so intense it runs like a high-speed burger machine. Behind every fresh, made-to-order meal is a massive factory system designed to deliver consistent flavor with zero shortcuts. In this documentary, we go inside the operation powering one of America's most iconic burger chains, from raw ingredients to grill-ready perfection. Unlike many fast food chains that rely heavily on pre-cooked, frozen, or highly processed food products, Five Guys has built its entire business model on quality, freshness, and simplicity. That simplicity, however, hides a remarkably complex and carefully controlled supply chain that delivers consistent, high-quality ingredients to thousands of restaurants across the US and internationally. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses, never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean to fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada, primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3 ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers, often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture, which allows it to hold up through the unique double frying process that Five Guys uses in-store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched, and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed, and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than +1 g. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun's structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use-by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated, but the buns are loaded in temperature-controlled staging areas and packed in sealed corrugated boxes to maintain freshness during transit. Any deviation in delivery, timing, or packaging temperature triggers a rejection at the restaurant level. In-store, the buns are stored at room temperature in designated bread racks, often rotated using FIFO principles. Staff members are trained to inspect buns visually and by touch. Any signs of excess firmness, moisture, or spotting lead to immediate disposal. Each bun is hand-prepared on-site, toasted on a grill with a light coating of melted butter before it becomes the vehicle for the burger build. This final touch, though simple, is only possible because of the structural integrity and texture delivered by the bakery's industrial process. Now that the core components of a Five Guys burger are accounted for, the beef, the fries, and the buns, it's time to examine the supporting elements that complete the burger experience: bacon, cheese, toppings, and condiments. These items may seem simple, but each is chosen and prepared with deliberate intent and, in most cases, centralized at an industrial level before being delivered to restaurants. Starting with bacon, Five Guys sources thick-cut, naturally smoked strips from approved pork processors in the US. The bacon is not fully cooked at the factory. Instead, it's partially cooked or pre-rendered to about 60 to 70% doneness, then chilled and vacuum packed in clear plastic pouches. These pouches are labeled and sorted by weight and count per case, with each case tagged for traceability. The bacon is cooked to completion in the restaurant, where staff lay it flat on the grill and crisp it to order. This two-step process, initial industrial cooking followed by final preparation, ensures food safety, flavor development, and grease reduction. The production of Red Bull starts long before the filling lines come to life. It begins at the sourcing and logistics stage, where each raw material used in the drink is carefully specified, contracted, and verified to meet the company's global quality standards. Although the ingredient list appears relatively simple: water, sucrose, glucose, citric acid, carbon dioxide, caffeine, taurine, B vitamins, and flavorings, the level of control and traceability involved in acquiring each component is remarkably complex. We begin with the most abundant ingredient: water. Water makes up the vast majority of the product, and its quality is absolutely critical. Unlike municipal tap water used in smaller food and beverage operations, the water used in Red Bull production must conform to pharmaceutical-grade purity standards. This means it undergoes extensive filtration, mineral balancing, and microbiological testing before it ever reaches the mixing tanks. In most Red Bull factories, water is drawn from deep, protected aquifers or dedicated water sources that are tested daily. The water is pumped into on-site treatment plants where it first passes through coarse filtration to remove particulate matter like sand or debris. It is then passed through activated carbon filters to strip away chlorine, organic compounds, or any remaining trace contaminants that could affect taste or chemical stability. The next step is typically reverse osmosis, a membrane-based filtration system that removes dissolved solids at a molecular level. This process reduces the water to an ultra-clean base, free of minerals, microbes, or off flavors. Once the water is purified, it enters holding tanks constructed from polished stainless steel. These tanks are fitted with level sensors, CIP spray heads, and temperature regulation systems to maintain stability. Water is kept in motion using gentle agitators or circulation pumps to avoid stagnation and ensure readiness for blending. Meanwhile, the sugar content of Red Bull, derived from both sucrose and glucose, requires its own specialized preparation. Red Bull uses a combination of these two carbohydrates to create its sweet but not overly cloying flavor profile. These sugars are sourced from sugar beets and corn and arrive at the plant either in dry crystalline form or as concentrated syrups, depending on regional supply chains. In facilities that receive dry sugar, the ingredient is pneumatically conveyed from delivery trucks into sealed sugar silos. These silos are climate controlled to prevent moisture absorption and equipped with weight sensors to track inventory in real time. When ready for production, the sugar is transferred to large dissolving tanks where it is combined with hot, purified water and mixed using high shear agitators to create a uniform syrup. This syrup is passed through mesh filters to remove any undissolved particles, then sent to a holding tank where it is cooled and held under sterile conditions. For glucose syrup, the process is slightly different. Delivered in bulk liquid containers or tanker trucks, the syrup is pumped through heated, insulated lines to prevent crystallization during transfer. Inline flow meters and viscosity sensors are used to ensure consistency. Once in the storage tanks, the glucose syrup is sampled and tested for pH, sugar concentration, and microbial stability before being cleared for blending. Now comes taurine, one of the most distinctive and chemically sensitive ingredients in the formula. Taurine is an amino acid-like compound that plays a role in neurological development and cellular hydration. It is synthesized in pharmaceutical-grade chemical plants through a controlled reaction involving ethylene oxide and sodium bisulfite, resulting in a high-purity crystalline powder. Red Bull does not extract taurine from animal sources. It is entirely synthetically produced for purity and consistency. Taurine is delivered to the beverage plant in sealed drums or lined bags inside rigid totes. Upon arrival, each container is inspected and sampled. The contents are tested for purity using high-performance liquid chromatography and screened for heavy metals and microbial contamination. Once cleared, the powder is either stored in a dry room or moved directly to the batching area, where it is weighed with precision down to the gram using automated ingredient scales. Caffeine, another central functional ingredient, is handled with similar precision. Synthetic caffeine, which is chemically identical to naturally occurring caffeine, is the preferred form in most facilities due to its purity and consistency. It arrives in fine white powder form, packaged in airtight containers to prevent oxidation and contamination. Like taurine, caffeine is dosed in tightly controlled quantities. Too much, and the drink becomes bitter or risks regulatory violation. Too little, and the expected stimulant effect may be lost. B group vitamins, specifically niacin, pantothenic acid, vitamin B6, and vitamin B12, are delivered in stabilized powder form. These micronutrients are highly sensitive to heat, light, and oxygen, so they are packaged in light-blocking, nitrogen-flushed containers. They are stored in temperature-controlled rooms and only opened at the time of production. Dosing is managed using micro-feeding systems, capable of adding quantities in the milligram range with high accuracy. Citric acid, used to balance sweetness and enhance shelf life, is one of the more straightforward ingredients. It arrives in either crystalline or liquid form, depending on plant setup. Like the sugars, citric acid is dissolved or diluted in purified water, filtered, and then pumped into blending tanks using stainless steel sanitary piping. It is included not only for flavor, but also to regulate the final pH of the drink, which has an impact on microbial resistance and carbonation behavior. The final core ingredient, prepared before blending, is carbon dioxide. Although it's added at the end of the line during filling, CO2 must be stored on-site in large insulated tanks under high pressure. This gas is certified food grade and must meet stringent standards for purity and dryness. Impurities in the gas, such as hydrocarbons or sulfur compounds, can result in off flavors or affect carbonation stability. Inline purifiers and moisture traps ensure that the gas remains within specification as it travels to the carbonation units. At this stage, all the major ingredients have been separately received, prepared, filtered, and stored in secure holding tanks, each one monitored by a network of sensors and controlled through a centralized process control system. The factory is now ready to enter the next phase, the blending and batch formulation process, where the base liquid is built step by step from these prepared components under tightly monitored conditions. Inside the blending hall of a Red Bull manufacturing plant, massive stainless steel tanks, often tens of thousands of liters in capacity, stand ready to receive pre-prepared ingredients. Each of these tanks is built with industrial mixers at the base and along the walls, with baffles designed to eliminate dead zones and ensure even distribution of all ingredients once mixing begins. These aren't just glorified vats, they're engineered systems with flow sensors, agitation controllers, and automated dosing inlets. Blending starts with the base, purified water. A calibrated volume is pumped into the blending tank. From here, the sweetener solution is added. By this point, the sugar and glucose have been dissolved into a consistent syrup in separate vessels and passed through fine mesh filters to remove any undissolved particles. They're now gravity-fed or pumped into the main tank through metered valves, which record the exact volume added in real time. At this stage, the solution is still colorless, with a mild sweetness and a viscosity slightly thicker than water. Stirring begins slowly, just enough to encourage circulation without aerating the mixture prematurely. Once the sweet base is established, the functional ingredients are added in a very specific sequence. This isn't just for convenience, it's chemical. Caffeine, taurine, and vitamins each behave differently depending on the pH, temperature, and concentration of the liquid they're introduced into. To ensure even dissolution, caffeine is dosed in carefully, often pre-blended into a neutral, aqueous solution to avoid clumping. Taurine, being more soluble, can be introduced directly, but at a steady rate to avoid localized saturation. The temperature of the blend is strictly controlled during this entire process, typically kept between 10 degrees C and 15 degrees. Keeping the temperature low helps prevent degradation of the heat-sensitive components, especially the B vitamins, and also limits the risk of microbial growth. Inline cooling jackets on the tank walls help regulate this, while digital sensors constantly send data to the factory's main control panel. After the active ingredients are in and fully dissolved, the next step is homogenization. While Red Bull is a clear drink and doesn't have oil-based elements like some emulsified beverages, this process is still used to ensure complete molecular distribution. A high-speed rotor-stator mixer is activated to subject the liquid to intense shear forces, ensuring that no microclumps or undissolved pockets remain. Think of this as the industrial version of making sure your recipe has no lumps, but at a scale where a few unblended grams could ruin an entire batch worth millions of servings. Once homogenized, the blend is passed through a fine filter system, often absolute rated filters that remove particles down to the sub-micron level. This is the final polish of the beverage, ensuring not just clarity and texture, but also eliminating any particulate matter that could interfere with carbonation or filling equipment. Now, the finished liquid base is sent to a storage tank, often referred to as the balance tank, which feeds the carbonation system. At this stage, the liquid is still uncarbonated. Carbonation must be done with surgical accuracy, both in timing and in gas levels. Too early, and carbon dioxide can escape during filling. Too late, and the drink will feel flat. Before carbonation, the balance tank contents are degassed using a gentle vacuum system to remove any dissolved air from the blend, air that could interfere with carbonation or introduce unwanted oxygen into the final product, leading to flavor instability over time. Carbonation is introduced through a high-precision saturator. This device uses temperature, pressure, and turbulence to force carbon dioxide into the liquid. The lower the temperature, the more CO2 the liquid can absorb, so the beverage is chilled further just before entering the saturator. Inside the unit, the liquid flows in a turbulent spiral while pressurized CO2 is injected. Sensors monitor saturation levels down to fractions of a gram per liter, and the flow is fine-tuned via automated valves. Once carbonated, the beverage is immediately transferred to the filler line. No storage, no delay. At this point, any agitation or exposure to heat could cause gas to escape, so the tubing, valves, and tanks are all designed to reduce turbulence. The product is now ready to be introduced into cans. Filling lines in a Red Bull factory are among the fastest and most technologically advanced in the beverage industry. The cans themselves arrive at the plant in stacks of blank aluminum cylinders, unprinted or pre-printed depending on the factory setup. These cans are depalletized automatically and conveyed upright to the rinser station. Here, they're inverted and sprayed internally with deionized water or sterile air to remove dust or particulates. From the rinser, the cans travel on a conveyor to the filler. This machine uses a gravity or counter-pressure system to fill each can precisely while preserving carbonation. The can enters the fill station, is sealed around the top rim with a flexible gasket, and then filled from the bottom up with cold, pressurized beverage. Fill levels are controlled within a margin of plus 0.5 grams to ensure legal compliance with net content regulations and consistent customer experience. Immediately after filling, the can passes to the seamer, where a pre-formed aluminum lid, known as the end, is dropped onto the top and crimped into place. This creates an airtight seal. Seamers are some of the most mechanically intricate machines in the entire facility, operating at speeds of over 1,000 cans per minute while performing multiple precision operations in less than a second per unit. After sealing, the cans are rinsed externally to remove any spillage and pass through a drying tunnel. They then enter the inspection phase. Here, cameras and sensors verify the seal integrity, check fill levels using X-ray or gamma ray detection, and inspect for dents, deformations, or labeling defects. Any can that fails inspection is automatically ejected from the line. Cans that pass all tests are conveyed to the packaging station. Depending on the market, cans are grouped in 4-packs, 6-packs, or full case trays. Robotic arms or mechanical pushers group the cans and slide them into shrink-wrap tunnels or cardboard sleeves. Once bundled, packs are palletized, either by layer robots or high-speed stackers, wrapped with stretch film and labeled with product codes, production date, and batch information. These pallets are now staged in a temperature-controlled warehouse, ready for distribution. The real-time tracking of every single ingredient, batch, fill date, and can code allows for full traceability from ingredient origin to final shipment. In the next section, we'll follow how those pallets move through the global distribution network and how Red Bull's quality assurance, shelf stability testing, and cold chain monitoring ensure that each can performs exactly as intended from Austria to Australia. With the Red Bull cans now filled, sealed, and packed onto pallets, the production process transitions into the next highly critical phase, post-production handling, distribution management, and long-term quality assurance. Although the drink is technically finished, the factory still bears significant responsibility for maintaining its integrity through storage, shipping, and shelf life. This phase involves coordinated warehouse systems, climate control, global logistics networks, and extensive quality monitoring procedures that extend well beyond the factory floor. All of it is designed to ensure that every can of Red Bull tastes and performs identically, whether it's consumed in Bangkok, Berlin, or Boston. Once the pallets are complete, they are conveyed from the packaging area into the outbound staging zone, a dedicated part of the facility built to manage finished goods. This area is laid out with barcode scanners, RFID readers, and automated warehouse software. Each pallet is scanned as it enters, recording not only the product type and production date, but also its batch code, can format, and destination market. This digital tracking ensures complete traceability of every pack produced. The system also flags any inventory that is out of rotation or that has not been cleared by the final quality audit. Pallets are stored in high bay racking systems that can reach 5 or 6 levels high. These racks are arranged to maximize airflow and minimize temperature variation, as environmental stability is critical for energy drinks. The warehouse is kept within a strict range of temperature, typically between 18 degrees C and 22 degrees C, and humidity under 60% to preserve carbonation, prevent packaging degradation, and protect flavor stability. Light exposure is minimized using tinted overhead fixtures or motion sensor lighting, since prolonged light can interact with the contents of clear or thin-walled aluminum containers, subtly affecting taste or causing internal discoloration. But before any pallet leaves the facility, it must be cleared through a final release protocol. This involves sampling from each production batch, typically 1 out of every few thousand units. These samples are sent to the in-house quality control laboratory for a battery of tests. Microbial testing is conducted to ensure that the beverage remains free from bacteria or yeast. Although Red Bull is not pasteurized, its low pH and high CO2 content provide natural protection, and the factory's sterile filling conditions act as a critical control point. Nonetheless, post-fill samples are incubated in climate-controlled chambers for 72 hours and checked for any microbial activity. Simultaneously, chemical stability tests are performed to verify that the concentrations of caffeine, taurine, sugars, acids, and vitamins are within tight tolerances. Each test is logged, reviewed, and signed off by senior lab technicians. Once the data passes review, the production batch is cleared for shipping. At this point, the factory releases the inventory into the hands of the logistics team, which organizes regional and international transportation. The Red Bull supply chain is designed around speed, efficiency, and protection. Because the drink is sold in more than 170 countries, it requires a global distribution system that can manage environmental variables, transit times, and regulatory differences across continents. Each factory or co-packing facility is paired with multiple logistics hubs, either operated directly or through third-party logistics providers, each specializing in cold chain monitoring, customs clearance, or last-mile delivery. Shipping conditions are tightly controlled. While Red Bull cans are shelf-stable and do not require refrigeration, they are sensitive to excessive heat and should not be exposed to prolonged freezing. Therefore, all transportation routes are mapped to avoid extreme temperature exposure. Trucks are preconditioned before loading, ensuring that their interior holds the correct temperature before the first pallet is moved in. During loading, factory staff monitor not just product count and pallet orientation, but also airflow paths and stacking height to ensure that cans are not crushed or deformed during transit. Each truck or container is equipped with temperature loggers and shock sensors. These devices record environmental data every few minutes and store it until offload. If a truck breaks down, or if the cargo passes through an area of extreme temperature fluctuation, the logs will show it. When the shipment arrives at its distribution center or regional warehouse, receiving teams will review the data. If it falls outside the acceptable range, the load may be held, inspected, or even rejected. This provides a full audit trail from the moment the product left the factory to its arrival at the next checkpoint. For international shipments, the process becomes even more complex. Export shipments must comply with country-specific food regulations. In some cases, ingredients must be declared differently. In others, labeling requirements vary. The factory works with regulatory teams to produce market-specific versions of the product, sometimes varying the language, caffeine content, or vitamin mix to meet local laws. Each international pallet is assigned a customs manifest, a certificate of analysis from the lab, and a temperature log that confirms it stayed within the specified range throughout the journey. Once Red Bull arrives at its destination warehouse, whether it's in Tokyo, Johannesburg, or Chicago, it enters a new round of inventory rotation and quality checks. Local distribution centers store the product under similar environmental controls, and the product is rotated using FIFO systems to minimize aging. While the drink has a long shelf life, usually around 18 months, Red Bull's internal standards aim to deliver most of its inventory to retailers within just a few weeks of production to ensure maximum freshness. Some pallets will be broken down into smaller loads and sent to large supermarket chains. Others are routed to gas stations, bars, vending machine operators, or e-commerce fulfillment centers. In each case, local merchandisers and sales teams monitor product placement, stocking practices, and display temperatures. Although Red Bull does not require refrigeration, many retailers choose to chill it for immediate consumption, and Red Bull provides branded refrigeration units to support this. At the store level, Red Bull continues to run random quality checks, known as in-market assessments. These include taste tests, packaging inspections, and code date verifications. Data from these assessments is sent back to the factory quality system and reviewed quarterly. If trends are observed, like subtle flavor degradation in warmer climates or denting during local transit, factory protocols are updated and packaging specifications may be revised. This feedback loop is critical to maintaining the uniform experience that Red Bull is known for globally. Even after the product has been sold, the process doesn't stop. Red Bull maintains traceability for every batch through lot codes printed on the bottom of each can. If a customer reports an issue, the quality team can pull that code, identify the exact production line, shift, and even the technician who oversaw that batch. While issues are rare, this system allows the company to investigate and resolve problems with precision, minimizing waste and protecting brand integrity. Beyond logistics and troubleshooting, the factory also conducts long-term aging tests. Retained samples from every production batch are stored under controlled conditions for 12 to 24 months. These samples are periodically tested for flavor consistency, vitamin retention, carbonation, and packaging durability. This helps inform decisions about shelf life labeling, new packaging materials, and product reformulation. Back at the plant, everything learned during distribution feeds into continuous improvement efforts. Engineers analyze transit shock data to refine pallet structures. Chemists review long-term flavor curves to tweak the balance of acids and preservatives. Operators attend refresher training sessions on fill line calibration, cap torque standards, and seaming pressure. The plant becomes not just a factory, but an evolving ecosystem of precision, designed to produce millions of cans with microscopic tolerance and global dependability. Inside Red Bull's production and R&D infrastructure, innovation continues quietly and continuously alongside the high-speed filling lines. While the mainstream drink is tightly standardized, parallel systems exist within the factory environment for development, testing, and controlled rollout of new variants, flavors, and formats. These operations are often confined to specialized pilot plants, small-scale, highly modular manufacturing lines where experimental recipes and new packaging concepts are trialed without disrupting the core production flow. These pilot lines mimic every critical phase of full-scale production, from batching to carbonation and filling, but at reduced volumes. Engineers can simulate the thermal and mechanical stresses of the full-size process, adjusting flow rates, temperature profiles, and equipment speeds to understand how small tweaks to formula or process could affect outcomes. Whether testing a sugar-free variation, a new flavor blend, or a limited edition can size, the data collected here determines what does and does not graduate to full factory rollout. Each new formula undergoes rigorous stress testing. Finished samples are subjected to cycles of heat, cold, vibration, and light exposure to simulate real-world transport and storage conditions. Flavor retention is tracked over time through sensory analysis and gas chromatography. Carbonation levels are monitored for stability across packaging types and temperatures. Packaging engineers assess how different aluminum can wall thicknesses or end configurations perform under pressure, especially when new recipes require modified CO2 saturation. If a variant clears all physical and chemical tests, the next step is consumer trials. In select cases, Red Bull collaborates with regional markets to test launch a new flavor or packaging size in a limited territory. These micro launches help measure demand, gather feedback, and identify operational issues before scaling up. Even then, these limited variants are often produced on flexible equipment lines reserved specifically for such runs, using interchangeable molds, modular filler heads, and smaller tank systems. Even small changes, like switching from a matte to a gloss label finish, require recalibration of the vision systems on the inspection line. Barcode scanners must be trained to detect label variations, and automated reject mechanisms must be tested to avoid false positives. This ensures no disruption in quality control, even when the product range temporarily expands. Back in the lab, teams also study ingredient interactions under extreme use scenarios. Industrial sugar production begins with harvesting, and depending on the region and facility specialization, the factory will receive either sugarcane or sugar beets. These two crops require distinct processes to extract sucrose, though many of the underlying steps, washing, crushing, juice clarification, and concentration, are similar in principle but differ in machinery, timing, and chemical inputs. Let's start with sugarcane. Sugarcane is a tall, fibrous grass grown in warm, tropical climates. It is harvested either manually, using machetes, or mechanically using harvesters that cut the stalks and strip the leaves in a single pass. Once cut, the cane begins degrading immediately, so it must be delivered to the processing facility quickly, typically within 24 to 48 hours, to preserve sucrose content and prevent microbial activity that would convert sugar into acids. The cane arrives at the factory by truck and is offloaded into massive intake yards. These yards are equipped with cranes or grab loaders that lift entire truckloads of cane and dump them onto conveyors that feed the primary cleaning line. Before any juice can be extracted, the cane must be washed to remove soil, leaves, and insects. This is accomplished with a combination of rotating drum washers and high-pressure spray systems that bathe the stalks in recycled processed water. The water itself is filtered and reused in a closed-loop system to reduce environmental impact. Once clean, the cane is conveyed to a chopper station. Here, high-speed rotating blades slice the cane into short sections to expose the inner fibrous material. The chopped cane then moves through a shredder, a powerful hammer mill type machine that tears the cane into finer particles. This dramatically increases the surface area of the plant material, making the sugar easier to extract in the next stage, milling. The shredded cane is now ready for juice extraction via mechanical milling. This takes place in a series of large, heavy-duty roller mills, typically arranged in a tandem line of 5 to 7 stations. Each station consists of 3 rollers, 2 lower and 1 upper, that compress the cane with immense pressure. As the cane passes through each station, more juice is squeezed out. Water is sometimes sprayed onto the crushed cane, a process called imbibition, to help wash out more sucrose during the final passes. The resulting juice, known as mixed juice, is a cloudy, pale green liquid that contains not just sucrose, but also fibers, proteins, organic acids, and soil particles. What remains of the cane after this process is a dry, fibrous residue known as bagasse. Rather than being discarded, bagasse is transported to a boiler house where it is burned as fuel to generate steam and electricity for the plant itself, often making the facility energy self-sufficient. Meanwhile, the mixed juice moves to the clarification phase. Before sucrose can be crystallized, impurities need to be removed. The first step is heating. The juice is pumped through a series of shell and tube heat exchangers to bring it up to around 105 degrees Celsius. This temperature helps precipitate some of the colloidal particles and also prepares the juice for chemical treatment. In the next stage, the juice is sent to a reaction tank where lime, typically calcium hydroxide, is added. This raises the pH of the juice and helps neutralize acids, precipitate proteins, and coagulate other impurities. The exact dosage of lime is tightly controlled using inline pH meters and flow-regulated injection systems. Flocculants may also be added at this stage to help bind the fine particles into larger clumps. After chemical treatment, the juice enters a clarifier, a large settling tank where gravity separates the solids from the liquid. The solids, known as mud, settle to the bottom and are periodically removed through rotary scrapers and pumped to a filter press where the water content is removed. The resulting cake is either composted or used as a soil amendment. The clarified juice, now a light amber color and much cleaner, is drawn off from the top of the clarifier and sent to the next phase, evaporation. Let's now consider the sugar beet process, which starts quite differently. Sugar beets are harvested using machines that dig them from the soil and remove most of the leaves and dirt. At the factory, the beets are washed in flumes, long channels of water that carry the beets through a series of mechanical washers and screens. Stones and heavy debris are removed using density separation, while fine silt is filtered out with mesh drums and hydrocyclones. Once clean, the beets are sliced into thin strips called cossets. These are fed into a diffuser, a long vertical or horizontal tank where hot water is sprayed over the beet slices. The water temperature is controlled to around 70 degrees Celsius and flows countercurrent to the beet material, maximizing sugar extraction. The sugar diffuses from the plant cells into the water, forming raw beet juice. This juice is then pumped to its own clarification stage, where lime and carbon dioxide are used in a process called carbonation. Calcium carbonate forms during the reaction and binds impurities, which are then filtered out, leaving behind a clarified beet juice ready for concentration. Both the cane and beet clarification processes converge at this point. They now have a clean, thin juice rich in dissolved sucrose. The next step in both methods is evaporation, which we'll explore in full detail in the following section. But for now, we've completed the complex, high-volume, highly monitored beginning of sugar manufacturing, where plant material is transformed, filtered, and chemically prepared for crystallization. Every moment of this phase is controlled with real-time feedback systems, mechanical separation equipment, and chemical treatments that must be perfectly balanced to set the stage for pure, white sugar to eventually take form. With the clarified juice now prepared, whether from sugarcane or sugar beets, the next major operation in industrial sugar production begins: evaporation. This process is designed to concentrate the diluted juice, which at this stage contains roughly 12 to 16% sucrose by weight, into a thick syrup known as thick juice or syrup, with a sucrose content of about 60 to 70%. The transition from thin juice to syrup is achieved by removing most of the water through a carefully staged thermal process. This concentration step is not just about volume reduction, it also creates the right conditions for crystallization to occur later with control and precision. Evaporation in a sugar factory is typically carried out using a multi-effect evaporator system. These systems are composed of 5 to 6 large vertical vessels, known as effects, connected in series. Each effect operates at a slightly lower pressure than the one before it, allowing the juice to boil at progressively lower temperatures. This setup significantly improves energy efficiency. Steam generated in one effect is reused to heat the next, conserving thermal energy throughout the process. The clarified juice enters the first effect and is heated with steam to just above its boiling point, typically around 115 degrees Celsius. As the juice boils, water vapor is released and rises to the top of the vessel, while the increasingly concentrated juice remains below. The steam from this first vessel is then routed into the heating coils of the second effect, where it causes the juice in that chamber to boil at a slightly lower temperature due to its reduced pressure. This cascading effect continues through all stages, progressively concentrating the juice without requiring additional high-pressure steam inputs at each stage. Throughout this process, automated sensors track the Brix value, sugar concentration, temperature, and pressure in each vessel. Flow controllers and level sensors regulate how much juice is transferred from one effect to the next, ensuring consistent residence time and thermal exposure. Operators monitor these values from a centralized control panel equipped with real-time displays and alarms. If any chamber's temperature deviates beyond acceptable limits, the system automatically adjusts steam input or juice flow to compensate. By the time the juice exits the final effect, it has thickened into a dense, amber-colored syrup with a viscosity similar to honey. It now contains upwards of 65% sucrose and has a reduced water activity, which helps to stabilize it against microbial spoilage. At this point, it's ready to enter the crystallization phase, a controlled process designed to coax sucrose molecules out of solution and into solid form. Crystallization begins in large, jacketed vacuum pans. These are vertical, cylindrical vessels where the thick syrup is further boiled under vacuum to lower the boiling point and prevent caramelization or degradation of the sugar. Reducing pressure allows boiling at temperatures around 60 to 70 degrees Celsius, preserving product quality. Inside each pan, agitators or stirrers keep the syrup moving, while high surface area heating coils provide uniform thermal input. The process begins with the introduction of a small amount of fine sugar crystals, called seed crystals or slurry. These seeds serve as nucleation sites around which sucrose molecules begin to gather and grow. The timing and uniformity of seeding are crucial. If seeded too early, too many crystals form, resulting in fine-grained sugar. If done too late, oversized or irregular crystals can result, affecting yield and downstream processing. Once seeded, the vacuum pan is held at a steady boil, and the syrup is gradually fed into the vessel in a process known as strike feeding. As more syrup enters, the crystals continue to grow while the water content is simultaneously reduced by evaporation. Operators closely watch the strike through sight glasses or by withdrawing small samples to examine crystal size and consistency under polarized light. When the desired crystal size and saturation level are reached, the strike is dropped, transferred to a large horizontal vessel called a crystallizer. Here, The mass, now called massacute, is gently stirred and cooled over several hours to allow further crystal growth and uniformity. The goal is to achieve maximum recovery of sucrose in solid form, leaving behind a thick mother liquor known as molasses. Once cooled and matured, the massacute is ready for centrifugal separation. Industrial sugar centrifuges are large, high-speed machines with perforated baskets that spin at up to 1,200 revolutions per minute. When the massacute is loaded into the centrifuge, the force of spinning flings the liquid molasses through the perforations, while the denser sugar crystals remain behind. Water or steam is sprayed onto the sugar during spinning to remove any residual molasses and improve crystal brightness. After spinning, the raw sugar is discharged from the centrifuge as damp, tan-colored granules. If the plant's end product is raw sugar, for example, in a raw cane sugar mill, this product is conveyed to dryers and then bagged or bulk loaded for transport to a separate refinery. However, in a full refining operation or beet sugar plant, further purification steps are carried out to produce white, food-grade refined sugar. The raw sugar is sent to a melter where it is dissolved in hot water to form a clear sugar liquor. This liquor undergoes multiple filtration steps, including activated carbon treatment and phosphatation or carbonatation, depending on the process. These methods remove colorants, organic compounds, and trace minerals. In the case of carbonatation, lime and carbon dioxide are added to form calcium carbonate, which binds impurities and is filtered out. After decolorization and final filtration, the sugar liquor is sent through a second crystallization stage, nearly identical to the one used for raw sugar, but this time targeting higher purity and clarity. The white sugar crystals formed in this process are sharper, brighter, and finer than raw sugar and are typically centrifuged, washed, and dried in a fluidized bed dryer. This dryer suspends the crystals on a bed of warm air that circulates through the granules, gently removing moisture without breaking the crystals. The final product is pure, white granulated sugar with a typical purity of 99.9% sucrose. It is cooled to ambient temperature and stored in silos constructed of stainless steel or food-grade plastic, protected from moisture and pests. These silos are equipped with temperature and humidity sensors, along with vibrating floors or fluidizing systems to prevent caking or compaction during long-term storage. From here, sugar can be packed into a wide variety of formats: retail-sized paper bags, industrial bulk sacks, or even liquid sugar totes, depending on customer requirements. All packaging is done in cleanroom grade conditions, using automated lines that fill, weigh, seal, and label each unit with production codes and batch tracking information. So far, we've followed the process from raw juice to pure sugar, navigating evaporation, crystallization, centrifugation, and drying. The next segment will explore how factories handle byproducts like molasses, manage energy usage with bagasse or beet pulp, and maintain food safety, quality assurance, and environmental compliance throughout continuous 24/7 operations. Now that the core crystallization and drying stages of sugar manufacturing have produced refined, food-grade white sugar, the final phases of the industrial process turn to three key pillars: byproduct management, energy and sustainability practices, and rigorous quality control systems that ensure every grain of sugar meets the specifications for purity, safety, and consistency. Modern sugar factories are not only high-output food production plants, they are also vertically integrated resource management systems designed to handle waste, generate energy, and produce multiple co-products with commercial value. Let's begin with molasses. After the centrifugation stage, once sugar crystals have been separated from the remaining syrup, what's left behind is a dense, dark, viscous liquid, molasses. This mother liquor still contains residual sucrose along with glucose, fructose, organic acids, minerals, and other non-crystallizable solids. The amount and composition of molasses can vary based on the raw material, cane or beet, the efficiency of crystallization, and the desired yield of refined sugar. In cane sugar operations, molasses is often drawn off after the second or third crystallization strike. Rather than being discarded, it's routed to molasses storage tanks, where it is either sold as a feedstock for ethanol distilleries or used as livestock feed due to its high energy and nutrient content. In some facilities, molasses is further processed to extract minor quantities of sugar through high-efficiency ion exchange or chromatographic separation, but this is only economically viable at large scale, or where sugar recovery is subsidized. In beet sugar production, molasses has a different profile, slightly lower in fermentable sugars, but rich in betaine and other organic compounds. It is also collected in holding tanks and transported in heated tanker trucks to fermentation plants, where it can be used in the production of yeast, citric acid, or industrial ethanol. In all cases, the molasses is handled under strict hygienic conditions to prevent spoilage or microbial contamination. Another major byproduct of sugar processing is bagasse, the fibrous, woody material left over from crushing sugarcane stalks. Rather than treating it as waste, factories utilize bagasse as a biofuel. It is burned in high-pressure boilers to generate steam, which is then used to power turbines that produce electricity for the entire sugar mill. Many sugar plants operate as self-sufficient cogeneration facilities, producing not only enough power for internal use, but also exporting surplus energy to nearby grids. Bagasse combustion systems are outfitted with flue gas scrubbers, electrostatic precipitators, and ash management systems to minimize air emissions and collect residual ash. This ash, in turn, may be used in agriculture as a soil amendment due to its mineral content, or it may be mixed with other waste materials to create compressed fuel briquettes. Some advanced mills pelletize dried bagasse for sale to industrial burners or biomass energy producers. Beet processing also generates fibrous residues, known as pulp. After the sugar has been extracted in diffusers, the beet pulp is pressed to remove excess moisture and then sent to drying systems, usually rotary drum dryers or flash dryers. The resulting dried beet pulp is then either pelleted or ground into flakes and sold as animal feed, particularly for cattle. High in fiber and moderately sweet, beet pulp is valued in the livestock industry for both energy and palatability. In both beet and cane facilities, the wastewater generated during washing, evaporation, and cleaning operations must be treated before discharge. Factories operate full-scale wastewater treatment plants that include sedimentation tanks, anaerobic and aerobic digesters, pH correction units, and sometimes membrane filtration. These systems are monitored continuously using turbidity sensors, chemical oxygen demand (COD) analyzers, and automated flow controllers. In some operations, treated effluent is reused internally for irrigation, ash quenching, or process water, further reducing the factory's environmental footprint. Solid waste is minimized through integrated process design. Soil and rocks from beet or cane washing are separated and sent to land reclamation or construction material applications. Boiler ash, as mentioned earlier, is either reused or compacted and safely landfilled. Filter cake from juice clarification, rich in organic matter and lime, is collected and sold as fertilizer, particularly in regions where soil pH management is important for crop health. Alongside waste handling and energy management, quality control is one of the most sophisticated systems operating inside a sugar plant. From raw material to final product, multiple checkpoints are established to measure, record, and verify key parameters. Quality assurance starts with raw material sampling. Upon arrival, cane or beets are tested for sucrose content, fiber, moisture, and purity. These values inform process adjustments and predict yield per ton of raw input. In the evaporation stage, bricks, soluble solids content, is measured at every effect using inline refractometers. These instruments use light refraction to instantly calculate sugar concentration in real time. Operators can adjust feed rates, heating input, or flow pressure based on these readings to maintain target consistency. During crystallization, samples are withdrawn at set intervals and examined under microscopes for crystal shape, size distribution, and purity. Technicians monitor the color using ICUMSA, International Commission for Uniform Methods of Sugar Analysis, standards, with high purity white sugar scoring under 45 ICUMSA units. If color values trend too high, indicating the presence of residual molasses, operators can make real-time adjustments to seeding rates or massacute concentration. After drying and cooling, sugar samples are run through particle size analyzers and moisture content meters. The particle size must fall within strict specifications depending on the final use. Granulated table sugar, for instance, has tighter specs than coarse industrial sugar, destined for beverages or confections. Moisture content is typically targeted below 0.05% to ensure long shelf life and prevent clumping. Final color, purity, and turbidity tests are logged digitally and associated with specific batch codes for traceability. Packaged sugar is subjected to additional inspection. Bags, sacks, or containers are weighed using high-speed check weighers that verify fill accuracy to within plus or minus 0.2% of the labeled net weight. Vision systems inspect print clarity, barcode legibility, and seam integrity. Packages that fail any of these checks are diverted and manually reviewed. Silos storing finished sugar are equipped with real-time inventory monitoring systems using load cells and level sensors. Temperature and humidity are also monitored to prevent caking or condensation. In some regions, silos are also flushed with dry, filtered air to reduce microbial risk in high humidity climates. Across the plant, digital SCADA systems pull data from all production stages. Operators view real-time dashboards showing flow rates, temperature curves, impurity removal efficiency, and steam usage. These systems not only ensure daily operational control, but also provide long-term analytics for performance improvement. Advanced factories even deploy machine learning tools that analyze historical data to predict maintenance needs or recommend minor adjustments to maximize recovery rate and minimize energy consumption. To comply with food safety and export standards, many sugar factories operate under ISO 22000, FSSC 22000, or BRCGS certifications. This requires documented hazard analyses, allergen control programs, cleaning protocols, and traceability audits. Every production lot is labeled with a batch ID that connects back to a full production record, raw input, processing conditions, lab results, and packaging date. Customer-specific requirements are also programmed into the system. For example, pharmaceutical-grade sugar used in oral medications must meet even higher purity and microbial specifications and may be filtered again through fine mesh screens and sterilized using UV or ozone treatments before final packaging. In some cases, sugar is converted into liquid form, known as liquid sucrose or invert sugar, by dissolving granulated sugar in heated, purified water and, in the case of invert, breaking down sucrose into glucose and fructose using acid or enzymatic hydrolysis. These liquid sugars are pumped into sterile tankers or IBCs, intermediate bulk containers, and shipped under temperature-controlled conditions to manufacturers in the beverage, dairy, or baked goods industries. Even at this late stage, the role of the sugar factory is far from static. Engineers continue monitoring consumption trends, regulatory shifts on added sugars, and regional demand to adjust capacity and format offerings. New packaging materials, biodegradable options, and energy recovery systems are constantly being evaluated and trialed, keeping the entire facility in a state of adaptive optimization. With refined sugar now stored in silos, bulk bins, or sterile containers, depending on its intended form, the focus turns to distribution, packaging, and how this versatile ingredient is tailored to the requirements of a wide array of customers, from retail consumers to massive industrial clients. This final stage is no less complex than the upstream processing phases. In fact, it involves its own dedicated systems for handling, labeling, traceability, and product customization. At this point in the factory, packaging lines diverge into three main pathways: consumer packaging, industrial bulk packaging, and liquid sugar dispatch. Each line is specifically engineered for its product format, and all are equipped with high-speed automation and real-time quality assurance systems. For retail products, such as granulated white sugar sold in 1 kilogram or 2-pound paper bags, the packaging line begins by feeding dry sugar through a vibratory chute into a vertical form-fill seal machine. The sugar passes through a flow meter and enters a funnel that drops it into a pre-formed bag made from food-grade paper or composite film. These bags are formed, filled, and sealed in one continuous motion. The machine prints batch numbers, expiration dates, and sometimes QR codes or traceability data on each bag. Each filled package passes through a metal detector and X-ray scanner to ensure that no foreign objects are present. Then, check weighers confirm that the net content is accurate within a narrow margin. Any under or overweight packages are automatically rejected and flagged for operator review. The approved bags are collected into bundles, often shrink-wrapped into 10 packs, and sent to palletizers that stack them for warehouse distribution. For industrial customers, packaging formats differ significantly. Sugar may be packed into 25 kilogram woven polypropylene bags, 50 kilogram sacks, or even 1-ton bulk bags called FIBCs, flexible intermediate bulk containers. These bags are filled using gravity-fed hoppers mounted on load cells that ensure weight accuracy.